Today in lesson 9.6, we will identify symmetry. Before, we reflected or rotated figures. Now we are going to identify line and rotational symmetries of a figure. Find the coordinates of the image of A, which is an ordered pair, -3, 8, for each transformation. Y equals X. So if you remember, the rule for Y equals X was AB becomes BA. So it's 8, -3. And the rule for the rotation of 90 degrees, AB becomes -BA. So B in the original figure is 8. That's -8. A is -3, -3. And find the coordinates of the image of -3, 8 for a translation 4 units down. That means X is not going to change. Your Y value is going to go down 4, so your new ordered pair is -3. A figure in the plane has a line of symmetry if the figure can be mapped onto itself by a reflection in a line. This line of reflection is a line of symmetry, such as M at the right. A figure can have more than one line of symmetry. So if I reflected this over M, I would have the same figure. So how many lines of symmetry does the hexagon have? This hexagon has 2 lines of symmetry. Basically, a vertical line and a horizontal line. This regular hexagon has 6 lines of symmetry. I don't know if you can, my drawing's bad there, you can see them here. And this figure C has just 1 line of symmetry. Do the objects appear to have? Okay. This one would have a line of symmetry, that'd be 1. That across there would be 2. That would be 3. That would be 4. That would be 5. So basically, if you kept spinning this around with the tip of the star, the ram would have 1 there. I'll try and draw these for you here in number 8, so you can see them. That's 1 line of symmetry. It's 2 lines of symmetry. 3 lines of symmetry. 4 lines of symmetry. Now that I have those, you might be able to see the others. 5, 6, 7, and 8. That last one is off a little bit, but I think you understand from my drawing what we're trying to show you. Draw a hexagon with no lines of symmetry. There's lots of ways to do this, but that would be an example there. Just a very irregular hexagon with no sides, congruent. You could do that and have a hexagon with no lines of symmetry. A figure in a plane has rotational symmetry if the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. This point is the center of symmetry. Note that the rotation can be either clockwise or counterclockwise. For example, the figure below has rotational symmetry because a rotation of either 90 or 180 degrees maps the figure onto itself. So So if you see, if I just rotate it 45, this is not going to be the same orientation or mapped on the same figure. If I rotate it 90 degrees, it has rotational symmetry. If I rotate it 180, it has rotational symmetry. So as long as if I can do a rotation of less than 180 degrees or less, and it maps it onto itself, it's considered rotational symmetry. So in this example, they're going to ask you, does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. So a parallelogram has rotational symmetry. The center is the intersection of the diagonals. At 180 degrees, a rotation about the center is going to map the parallelogram back onto itself. And this regular octagon has rotational symmetry. The center is the intersection of the diagonals. In this case, a 45 degree, a 90 degree, 135, or 180 degree rotation about the center all map the octagon onto itself. A trapezoid does not have rotational symmetry because no rotation of 180 degrees or less maps the trapezoid onto itself. Do the figures have rotational symmetry? If so, describe the rotations that map the figure onto itself. So a rhombus has rotational symmetry 180 degrees about the center. The octagon, this octagon, has rotational symmetry if I rotate it either 90 or 180 degrees, either direction, clockwise or counterclockwise, about the center, the figure is mapped onto itself. The right triangle does not have rotational symmetry. Identify the lines of symmetry and rotational symmetry of the equilateral triangle. Okay, here are your choices. 3 lines of symmetry with a 60-degree rotation, 3 lines of symmetry with 120 degrees rotation, 1 line of symmetry 180 degrees, one line of symmetry, no rotational symmetry. The triangle has line symmetry. It's an equilateral triangle. 3 lines of symmetry can be drawn for the figure. For a figure with S lines of symmetry, the smallest rotation that maps the figure onto itself has the measure 360 divided by S. So 360 degrees divided by the 3 lines of symmetry means it has 120 degree rotational symmetry. So the correct answer is B, 120 degrees rotational symmetry. So you can always use that formula, okay? 360 divided by the lines of symmetry. We talked about an equilateral triangle. Now we're going to talk about an isosceles triangle. So picture an isosceles triangle here. And if you picture it, it makes it easier for it to see. It has no rotational symmetry for a non-equilateral triangle. The altitude is the line of symmetry. How many lines of symmetry does each figure have? A rhombus that is not a square. I think we've seen this one before. Okay, has 2 lines of symmetry. We've talked about it having rotational symmetry, and 180 degrees has 2 lines of symmetry. How many lines of symmetry does this figure have? We've already talked about this one also. An equilateral triangle has 3 lines of symmetry. Does the figure have rotational symmetry? If so, describe the rotations that map the figure onto itself. I think you can see it. It has rotational symmetry. It actually has 5 lines of symmetry And as we had that formula before that we talked about, 360 divided by 5 is 72. So 72 and 72 times 2 is 144. So as rotational symmetry, it's 72 degrees and 144 degrees. And this figure, look here, that's not it, right? That would not be it. But it would have a line of symmetry right here, but it has no rotational symmetry. To help you out, here are the problems from which your homework is from. This is a fairly simple lesson today.